You're not going to work, are you? Okay, great. This is working. So today we are looking at the second way we use to determine the rate law of a reaction in our kinetics unit. If you remember from last class, we know how to use a mechanism to figure out the rate law, and that was going to the slow step of a mechanism, taking the reactant's concentration and raising them to the power equivalent to the coefficient in front of them in that slow step. Well, today we're going to look at a second way called method of initial rates, and method of initial rates is a system that requires actual data for us to figure out the rate law and analysis of that data. So here in the method of initial rates, you have typically two or more experiments are run where the initial concentrations of all the reactants are changed, and then after doing some experimentation with those concentrations, the initial rate is determined, and that's where we get method of initial rates. Sometimes people say MOIR to indicate method of initial rates. And once we have those methods of initial rates, a table is created. You guys will not be responsible for creating the table. This is what a typical method of initial rates table looks like. Notice we have multiple experiments. We have concentrations. These are starting concentrations, and the initial rate of the reaction as soon as the reaction starts. And so 3 different experiments were done. Data was collected and put into the table. So the first order of business in something like this is to, in order to do the rate law, is, as I always call it, write the skeleton of the rate law. You already know from previous classes that a rate law is always rate being equal to some constant times the concentration of our reactants. In this case, it's concentration of NO2 raised to some power that we call order, times the concentration of the other reactant raised to some other power. For ease, we're going to call that just X and Y. So the first step to this is we're going to look at these and do ratios of experiments in order to find some of these powers. First thing you do is pick 2 experiments where one of the concentrations doesn't change. Now this is real life data, so I'm going to start with experiment 1 and 2. In experiment 1 and 2, you can see that they have pretty much the same concentration. Since it's real life data, you're probably not going to have the exact concentration, but that's pretty much close enough. So I'm going to start, and I'm going to take one experiment and divide it by another. What do I mean by that? I'm going to do a ratio of the experiments. I always like to put the experiment with the larger rate on top. I'm looking at experiment 3:1. So I'm just writing this down for reference. What I'm going to do is take everything that I know from experiment 3 and put it into the skeleton rate law. So my rate is equal to 7.57 times 10 to the negative 3 K times, and again, I'm just going to experiment 3 and plugging in everything that I know. I don't know the order yet. That's the job I'm doing right now. And then I'm going to plug in my other little guy here, and that's experiment 3. All right, and I'm going to divide that by the same information from the table for experiment 1. Why am I choosing those 2 again? Because these 2 concentrations are the same. So for experiment 1, I get 1.90 times 10 to the negative 3 is equal to K times 0.0482 to the X times 0.0318 to the Y. So if you notice with this ratio, I can cancel stuff out. My K's are going to cancel. I'm literally treating it like a quotient. And then 0.0482 to the X is pretty much the same here in both cases, so that can cancel. So what I need to do now is use my calculator, and I'm going to divide. And because I'm putting it into this formula, into this equation, and dividing one by the other, I call it the ugly algebra method. So us plugging in all those numbers makes it ugly algebra. I'm going to show you a different way to do it next. But when I divide 7.57 e negative 3 by 1.90 e negative 3, I get 3.98. And that's going to be equal to what I'm going to do here is divide 0.127 by 0.0318, and when I do, I get 3.99, and that is to the y. So, math is hard. What's y? What power is that? Y is equal to 1. So that means this is first order with respect to, which one did we not cancel out? It was the F2, right? So the F2 is going to be first order with respect to that reactant. And so now that you kind of see this, you can see why now we choose 2 experiments where the concentration is the same. Since this concentration is the same, we know that it itself is not affecting the rate change. It's only the F2 that's affecting the rate change. So we look at how mathematically that affects it. Okay? So that's how I found the order with respect to F2. So now I'm going to try to find the order with respect to our next little guy, and that is going to be, we're going to have to keep 2 other experiments constant where the other one is held the same. And so here F2 is held the same. So in our next thing, and I'm going to go to another slide, and this is not going to be in your view anymore, but we are basically going to put the bigger one on top. So we're going to do experiment 1 over experiment 2. So you're going to want to try to fit all of this on one page, hopefully. So going to the next page, I put in a blank page here, we are going to now put experiment 1 over 2. And in experiment 1 over 2, I have 1.90 times 10 to the negative third is the rate, and I'm plugging it into the same skeleton, is equal to 0.0482 to the x and 0.0318 to the y. Or I could put 1 in there. It doesn't matter. Now that I know it's 1, because I did it from the previous math we did, I got that from that math. And then I get 4.69 times 10 to the negative fourth. This is experiment 2. K times 0.0120 to the x times 0.0315 to the y, or to 1, same thing. Notice these guys are going to cancel again, and then this is going to cancel. And so when we divide 1.90 times 10 to the negative third by 4.69 times negative fourth, we get 4.05, and then that's going to be equal to 0.0482 divided by 0.0120, giving us 4.02 to the x. So x is also equal to 1. So this is not a very fun one, is it? X is equal to 1. And so this is first order with respect to NO2. So just note, in order to get credit on the AP, you can't just say, oh, X is 1 and be done. You have to indicate what order, or sorry, which reactant the order that you just solved for is relating to. So you always want a statement like this, first order with respect to NO2, and we also now know it's for first order with respect to F2. So let's go to, the next page. Determine the overall order. Overall order is always equal to the sum of the individual orders. So we had first order with respect to F2, first order with respect to NO2, so our overall order is second order overall. Now, the answer to this question is going to differ depending upon the order that they, order not like order, depending on order as in which came first, what order these two come in. If the first question they ask is the rate law, you're allowed to leave the K as just a plain letter and just write NO2 to the first times F2. A lot of students feel they need to solve for K, which we're going to do in the next question, and then they feel like they have to go back and put that value in. If they ask you to solve for K first, then you would put the numerical value in for K. But since the first thing they asked you here was for the actual rate law, you can leave K as a letter. But if we want to actually calculate K, what we're going to do is just pick any of the three experiments, plug in rate, the concentrations, and raise them to the appropriate orders and solve for K. So with this first one, we are going to say, I always take experiment 1 for ease. I suggest you do as well, because on the AP, they typically use experiment 1 for their key. It's not required, but if you did your problem right, they should all come out pretty dang close. And then F2. Some textbooks tell you to find the K for all the experiments and then average them. Please don't do that. It's just a waste of time. All right, so I'm going to plug that in, and now I'm just going to solve for K mathematically. One thing that's important, this is a K, little k, for kinetics, where units are crucial. We have to have units on this. So I'll talk about the units in a second. Right now, if I mathematically solve and do just that divided by that divided by that, I end up getting a K of 1.24. You guys can check my math and make sure I'm not crazy. But again, units are always required. You will not get credit unless you include units of K. So you can do one of two things. You can do old-fashioned solving for units. Molarity over second is the unit on rate. How did I know that? I looked at the table. Here it's molarity, here it's molarity. So if you just do the steps in algebra, you're taking molarity times seconds divided by molarity, so that's 1 over seconds, divided by molarity again gives you 1 over second molarity. That's easy in this case because the orders aren't very high, but it tends to get a little bit confusing, so there is a shortcut to that, which I highly suggest that you pay attention to. The shortcut for the units is 1 over the unit of time times to the molarity raised to the power of the overall order minus 1. That's the shortcut. So let's look at it. 1 over our unit of time. What's our unit of time? Look at the table and notice that the rate is per second times molarity raised to 1 less than the overall order. Our overall order was 2, so 1 less than that is 1. So this is going to be a really, really helpful shortcut later for determining the units on K. All right? So that's all you do. It's not really hard. The next one I'm going to do with you, I'm going to use the inspection method. We're going to look at the table and kind of come up with the same idea. We're basically taking numbers that are easier and doing the math in our head. And if the numbers are easy, you're allowed to do this. And I'm going to show you what's required so you don't have to show all that work to get credit. So again, this is a method of initial rates problem because I've got different experiments. I've got initial rates. Now notice I have pressures here instead of concentrations. What's the deal with that? Well, I want you to remember, and we kind of talked about this last semester, that there is a proportionality between pressure of gases and their concentration based on the ideal gas law. So notice if I take this and divide both sides by V, I get this. This is a constant. So pressure is proportional to moles over volume, which we know is molarity. And this is only in gaseous systems. So all these things, notice up here, are gases. So this is, you treat those pressures exactly like you would treat concentration. So instead of all the ugly algebra, we're going to do table logic. So when you do table logic, again, you're going to pick 2 experiments where one of the pressures or molarities isn't changing. So I'm going to pick experiment 1 and 2. Now, that means these aren't changing, right? So when I'm solving here, I'm looking for the relationship between the hydrogen concentration / pressure and the initial rate. So as I go from here to here, what did I do to the pressure? I doubled it, all right? As I go from here to here, what did I do to the initial rate? I doubled it. What power do I raise the pressure to get a double in rate? What exponent would that have to be? So we know that 2 to the 1 is equal to 2. So that exponent is 1. So this is first order with respect to H2. Now, the question is that enough to get credit on the AP? No, it's not. What you have to do is state the following. As the pressure of H2 doubles, what happened to the rate? The rate doubles. Therefore, it's first order. And that's all you need to say. Okay, but you have to show that you understand the relationship between that guy and that guy. All right, so let's look at 2 more experiments. In these 2 experiments, we're keeping the H2 constant, and as we double the NO2, the NO, what do we have to raise it to, what did we do there? Quadruple. We quadrupled it. So what power do we have to raise? See, not everything's first order. I was hoping that you wouldn't make that assumption. So as we doubled the concentration, the rate actually quadrupled. So this is second order with respect to NO, because as the pressure doubles, the rate quadruples. So what's with the zero order we talked about last class? Zero order meant it was in the overall reaction, right? The reactant was there, but it didn't affect the rate. If you had something that was zero order, you'd see it change in your concentration, but the rate would stay the same as well. So what that would mean was no matter how we changed our reactant, it had no effect on the rate. Therefore, it's zero order, which means it wasn't in the slow step of the mechanism. So just know that that is going to be a possibility. So this is therefore, kind of went off on a tangent there, therefore second order. Okay, so those are the way that things that the manner at which you are going to most likely have to solve using one of these two. They're not going to be much more difficult than that. Let's finish this problem up a little bit. Determine the overall order of what we just did. Well, the overall order of what we just did was 2 plus 1, right? So this is third order overall. Write the specific rate law, rate. Be careful here, because it's not a concentration. I do not want you to use brackets. I need you to use parentheses and raise it to the power and do a pressure with a subscript like this. This is the form it needs to be in. Do not use brackets because they are not concentration. So when we're solving for that K, which is the next part of the question, I'm just going to take experiment 1 data, and I'm going to get 400 squared times 150 to the first, and I get a number of 2.8 times 10 to the negative 8. So forget the whole algebra thing. I'm just going to do the shortcut. 1 over, what is my unit of time? If I look on the table, it said seconds again. Times, in this case, it's not molarity, right? It's millimeters of mercury. So it's pressure raised to 1 less than the overall order. The overall is 3, 1 less than that is 2. And that would be the rate constant including units. So when in doubt, or if you really don't get the shortcut, you can just go ahead and say, okay, this is millimeters of mercury over seconds. This is seconds, and that's seconds. So millimeters of mercury divided by seconds squared is millimeters over, no, not seconds, my bad. This is not time. This is millimeters of mercury squared and millimeters of mercury. All right, so if we divide 1 over millimeters of mercury over seconds divided by millimeters of mercury squared divided by millimeters of mercury, we get 1 over seconds times millimeters of mercury squared. So you can do it the shortcut, or you can do it looking the algebra way. All right, this problem, honestly, you will not get something like this on the AP. I am going to work through it because it introduces a couple concepts. You not having enough reactants, the same concentration, to cancel things out. It also shows you the concept of fractional order, which doesn't make sense, really, if you think about it. Remember, order is how many of those molecules are slamming to each other in the slow step of a mechanism, so how can half of a molecule slam into another one? We're going to talk about that more specifically in equilibrium. So right now, I just want you to be a monkey and solve for this without thinking too much about the y on the fractional coefficient. So starting this, again, if you are freaking out at this point, because I'm not here, and you just get to hear my voice and not actually ask me questions, this is the last thing I want you to worry about. I want you to go back, listen to the first 2 examples again and again and again until you understand it. This one is kind of icing on top of the cake. If you can do this, you are golden and basically are ready to roll when it comes to these kinds of problems. So what I want to do is start with our number 2 over number 1. Why am I choosing 2 over 1? Because if you notice in this, both of those are kept constant, so the only thing that's changing is this one. So I'm choosing 2 because to go on top because 2 is greater than 1, right? I'm trying to find, I've lost something and it makes me sad. Okay, so looking at this, we're going to put experiment 2 over experiment 1. 8, so starting with our rate, let me go ahead and write the skeleton first. That might be the way to roll. Rate is equal to k times a to the x times b to the y times c to the z. All right, so again, I'm picking those first 2 experiments because they are experiments where the 2 of them are kept constant. So I'm going to plug in 2 over 1. So my rate of 2, here we go, 1.19 times 10 to the negative 2 is equal to k times 8.71 times 10 to the negative 2 to the x times 2.50 times 10 to the negative 2 to the y times 4.00 times 10 to the negative 3 to the z. All of that over experiment 1, which is 1.74 times 10 to the negative 4th, is equal to k times 1.05 times 10 to the negative 2nd times, and these are the same, right? We're canceling them out, so just doesn't matter because they're the same. So these are all going to cancel, right? And our k is going to cancel. Now, some of you are still probably wondering, why does she want to put the one with the larger one on top? I'm only doing it to make the final solving for that exponent easier. I think it's easier to use an exponent to solve for a number greater than 1 than to solve for a decimal or a fraction. I'm not that math savvy, and I'd much prefer whole numbers or numbers greater than 1. So when I divide these two things, I get 68.39 is equal to, and I divide this, I get 8.295 to the x, so I just divided those two numbers. When I put this in my calculator, pretty gosh darn close to 2. So x is equal to 2. So this is second order with respect to a. So the order with respect to a is 2. All right, so now I got to figure out what am I going to do for the next one, because I can't find a situation here where I have concentrations that are the same for 2 others. So I see here I've got 2 concentrations. I can't do this one again because I already compared 1 and 2. So I've got to compare 2 different ones. So I feel like I'm stuck. I'm like, oh, I only know this. Well, here's the deal. You know this, right? So that can be canceled out eventually when you do your math. What else do you know now? You know the order that goes in here. So we're actually going to plug our order in and solve for a numeric value and divide that numeric value. So I'm just going to show you how to do that. That means I'm going to, and I'm going to go to the next page here in a second, but because I have this set up like that, I'm going to put 4 over 3, just so you know. This is a bigger rate, so I'm going to put experiment 4 over 3, and I'm going to show you how I can use that to get the order then of the one that I don't know anything about, which is C. So I'm going to use this 4 over 3 to find the relationship for C. Okay, I'm going to do that on the next page. So 4 over 3. So let's start. 4's rate, 7.58 times 10 to the negative 3rd is equal to k times 4.20 times 10 to the negative 2nd squared times 2.1 times 10 to the negative 2nd to the y times 4.2 times 10 to the negative 2nd to the z. Divide all of that by experiment 3, which is 1.34 times 10 to the negative 3 is equal to k times 2.10 times 10 to the negative 2nd squared, because I know that from what I solved for in my first part. This is going to be the same. And then this one is 2.1 times 10 to the negative 2nd to the z. Well, this cancels now, right? Now, this whole thing right here, this doesn't cancel, but it's a number, right? So I'm going to cancel this out, and then I'm going to go ahead and do my division. So when I divide 7.58 e negative 3 divided by 1.34 e negative 3, I get 5.66 is equal to, now if you notice, 4.2 divided by 2.1 is 2, but it's squared, right? Which is going to then be multiplied. This cancels. So now looking at my z's, I get 4.2 divided by 2.1 is 2 to the z. So now what I'm going to do is take my 5.66 and divide it by this 4 here. So I get 1.41 is equal to 2 to the z. Okay, all of us know what 1.41 is, right? What is that? The square root of 2, correct? So what is the value then for that x? Square root is half. So z is equal to 1/2. So this is half order with respect to which guy? It was to c. So now we know our c is 0.5. All right, so how does that help us? Let's go back to the table. Now we've compared 3 and 4, correct? We've compared 1 and 2. Now we have to pick a combination that we haven't used yet. At this point, I don't really care which ones you use as long as it's not 1 and 2 or 3 and 4. Just looking at this for ease, I'm going to go ahead and randomly just compare 2 to 3. Because what we want to make sure, the only thing you need to watch out for is that the two things you're comparing for the missing one, we haven't found B yet, so we want to pick two experiments where B is different, because that's the one we have yet to find. We know the coefficients for this guy and this guy, so these are going to turn into numbers, and we'll solve for that exponent on B. So I'm going to do experiment 2 on top of experiment 3. I'm going to do it right here, 2 over 3. All right, so plugging all that in, here we go. 1.19 times 10 to the negative second is equal to k times 8.71 times 10 to the negative second squared times 2.5 times 10 to the negative second to the y, because we don't know that one, and we know this one is 0.5. 4 times 10 to the negative third to the 0.5. Thank goodness for calculators. This would be one you would never, ever in a million years be able to do with ugly algebra. With inspection. You have to do ugly algebra and you have to use your calculator, unless you're Rain Man, and some of you might be. Some of you don't think math is hard, like I do. 1.34 times 10 to the negative third is equal to k times 2.10 times 10 to the negative second squared times 2.10 times 10 to the negative second to the y times 2.10 times 10 to the negative second to the 0.5. So now, the only thing I really can cancel is that guy. So everything else becomes a number. So in my world of numbers, I've got 8.88 is equal to, when I divide these two numbers, 8.71 e negative 2 squared divided by 2.10 e negative 2 squared, I get 17.20. All right? And then now I'm going to have something that has the exponent. So I'm going to divide this number by that number, and I get 1.19. But remember, that's going to be to the y, according to some sort of math rule. I don't know what it's called. And here I'm going to divide 4 e negative third to the 0.5 divided by 2 e negative 2 to the 0.5, and I get 0.4364. And again, guys, if you're freaking out, it's never going to be this hard on the AP. I'm giving you the master problem here. If you can do this, you're golden. And so here I get 1.18, and I'm dividing that 8.88 by this and by this, and I get 1.19. Oh, look how nice that worked out. So what is that? Y is equal to 1. So this is first order with respect to B, or not to be. Get it? Kidding. All right, next. I don't need the third page. Determine the overall order. Well, we've already kind of done this, right? 1 plus 2 plus 1/2. So our overall order is 3.5. Write the specific rate law. Rate is equal to k times a to the 2 times b to the 1 times c to the 0.5. And then determine the rate constant. This is a long one. 1.74 times 10 to the negative 4 is equal to k times 1.05 times 10 to the negative 2 squared times 2.50 times 10 to the negative 2 to the first times 4e negative 3. I can't believe I wrote an e. I'm just like physics. That's horrible. I'm doing it because I was out of room. That's the only reason I do things like that. We end up doing math on the right, and we get k times, when I do all that math, I get 1.74 times 10 to the negative 7th. All right, and so I end up getting a k value of 998. Now, I definitely don't want to do the math on all these crazy half-unit stuff. I'm going to do my shortcut. My unit of time, according to the table, was seconds. 1 over seconds times molarity raised to 1 less than the overall. The overall is 3.5. 1 less than that is 2.5. And so that is all there is with method of initial rates. Not too hard. Very last thing I want to show you, this is really nothing in regards to finding a rate law. However, it's something called instantaneous rate. I'm not 100% that it's not going to be on the exam. I can't see it in the curriculum, but I will go ahead and just make you privy to this. So instantaneous rate is the rate at any one point during an experiment. So when we start an experiment, up here is the concentration of a reactant. It doesn't really matter which reactant we're talking about. And it makes sense that as time progresses, our concentration is going to drop, right? Totally makes sense. If we want to know the instantaneous rate, what we're looking for is basically the rate at any one particular time. So let's say that someone wanted to know the rate of the reaction after 8 minutes has passed. To find the instantaneous rate, all you would do is you'd go to 8 minutes, go on the curve, and draw a line tangent to the curve at that point, and find the slope of that line. The slope of that line is the rate at that time. Why is the slope a rate? What is slope? Change in y over change in x, right? Change in y is our change in concentration, and then change in x is our change in time. Isn't change in concentration over change in time a rate? That's the rate we look at in kinetics, right? How much the concentration changes over a certain time. So the slope of the line tangent to the curve at that time is the instantaneous rate at that time. Those of you in calculus are probably going, yeah, we already know what that is. You're doing it, baby. What is it actually called in calculus? You guys know it's the derivative, right? If you don't know calculus, you're fine, because you can figure out just by drawing the line and doing good old-fashioned delta y over delta x, you can figure out that slope. You don't need to know a lick of calculus to do that problem. If you decide you'd like to assign variables and arbitrarily solve for this using calculus, you are going to be allowed to do that. I might have to go to a math teacher to verify what you're doing is correct, but I think I could probably figure it out. So whichever way you want to solve for instantaneous rate is cool. Again, not too concerned about this because it's not technically referred to in the new curriculum, but I could see them maybe asking some minuscule questions about it. All right, I hope you paid attention. Now that we're at the end of the video and I'm not here and you think that because I'm not here you don't need to know this information, you are sorely mistaken. So you might want to go home then and rewatch it, because I'm holding you accountable for every single thing on this video. I'm going to come back next class and expect you to be ready to move on with information regarding this. So your homework is due. Stick to the calendar, look at the calendar. If you have any questions, you can shoot me an email.